Warahmatullahi taala wabarakatuh. My name is Arif Hakimi bin Ali.
And my name is Muhammad Fidaus Naim bin Azlan Shahrin.
Alright. So today we would like to present our project for NMT 22104 subject, which is development of an autonomous self-balancing robot with dynamic PID control and obstacle handling strategy. Okay, so our project is basically is a two-wheel self-balancing robots which utilize PID control to stabilize their inherently unstable inverted pendulum design, and they are increasingly used in personal transport and industrial automation. So this project integrates this self-balancing platform into a robotic sumo framework, evaluating how stability algorithms adapt to physical collisions and real-time load changes as the robot dynamically detects and clears obstacles.
Okay, for problem statement, balancing drift. The IMU sensor MPU 6050 is highly susceptible to noise and data errors, causing the robot to tilt or drift if initialized on uneven surface. Next, instability during pushing. Physical reaction force during obstacle pushing and disrupt the control system, causing the robot to overtilt and quickly fall over.
Okay, so we have three main objectives, which is first is to design and develop a functional two-wheel self-balancing robot utilizing an ESP32 microcontroller and MPU 6050 IMU. The second is to implement a proportional integral derivative PID control algorithm tuned to maintain the vertical stability of the robot. And for the third is to integrate an HC SR04 ultrasonic sensor with an incremental set point shifting logic that enables the robot to detect and push obstacles while it while keeping its balance.
Okay, for scope of project, hardware configuration. The prototype utilized an ESP32 dev module as the main control, integrating an MPU 6050 sensor for tilt angle feedback and HCSR04 ultrasonic sensor for obstacle distance scanning and L298N driver to control to DC gear motor. Software implementation program in C++ within the Arduino IDE. The software utilized the standard PID V1 library and a non-blocking ultrasonic reading method to maintain uninterrupted timing for the balancing loop. For operational limitation, designed for flat surface, the robot continuously execute its automated pushing behavior as long as an obstacle is detected within its strict 20 cm frontal range.
Okay, so there are four expected outcomes. For the first one is the robot should have stable stationary balance. So the robot must seamlessly maintain a stable drift-free upright position on flat surfaces without requiring any physical support. Next, responsive and non-blocking object sensing. So the ultrasonic sensor must accurately measure obstacle distances up to 20 centimeters in real time without causing delays to the high frequency PID balancing loop. And next is the robot must continuous balance forward pushing. So upon detecting an object, the robot must execute a smooth set point shift to forcefully push the obstacles forward while the PID loop dynamically adapts to prevent the chassis from falling. And for the lastly is practical engineering competency. So basically, this project aims to enhance the developers, which is us, practical skills in tuning real-time control loops, mathematically filtering sensor noise, and programming multi-behavioral state logic in embedded system.
Okay, for software and hardware, first hardware ESP. We use ESP32 microcontroller board, MPU 6050 IMU sensor, L298N motor driver module, ultrasonic HCSR04 sensor, infrared IR sensor, DC motor, lithium ion 18650 batteries and battery holder. For software, we use Arduino IDE for coding, Proteus for schematic.
For the experimental result, for PID tuning and experimental observations. Experimental method. The closed loop recovery speed of the prototype was evaluated by applying minor manual taps during a trial and error PID tuning process. Proportional, which is KP tuning. A baseline of KP of 32.5 was established because lower gains resulted in immediate falls, while higher gains triggered violent overshoots and rapid oscillations. For derivative KD, damping, an optimal KD of 0.85 was chosen to introduce sufficient damping against swaying, whereas excessive KD values such as 1.0 cause unstable high frequency shaking. Next, integral KI optimization. Adding KI significantly reduced steady state error and enhanced drift resistance, though Dove pushing the gain to 200 cause aggressive motor overcorrection and failure. And final optimal configuration, the optimized parameters of 32.5, 180.5, and 0.85 achieve a swift 1.8 second settling time, delivering perfect balance, zero drift, and rapid recovery from disturbance.
Okay, for discussion, the discussion demonstrate that while the optimized PID controller and three-tier physical layout successfully achieve a rapid 1.8 second dis- disturbance recovery with smooth multitasking, maintaining battery level above 7.4 volt and implementing static software calibration, vital to overcoming inherent mechanical backlash and sensor drift.
Okay, so for the conclusion, the autonomous self-balancing robot project for the NMT 22104 course was successfully completed. The project successfully integrated physical mechanical design, multi-tier hardware isolation, and discrete feedback control loops using the ESP32 platform to demonstrate control systems engineering in automation. The evaluation of the project confirms that all research and development objectives were successfully achieved.
For the recommendation, uh, first upgrade to encoded stepper motor, replace the plastic ear DC motor with high torque stepper motor and quadrator encoder to completely eliminate mechanical backlash and achieve precious stability control at low speed. Okay, next, implement intelligent power regulation. Add an active buck boost voltage regulator circuit to maintain a constant current supply to the motors, preventing balance and stop degradation when the battery voltage drop below 7.4 volt. Lastly, integrate site proximity sensor. One additional time of flight TOF or secondary IR sensor on the left and right side of the chassis to expand the robot obstacle detection field of the view to 360 degrees.
Okay, so this is our video of the tournament past day. Yes, so first obstacle is going down. So next. Alright, next obstacle is going down. Okay, that's all. Alright, so that's all from us. Thank you and Assalamualaikum.